Hello, I'm Mike. I'm a PhD student at Monash University, primarily interested in binary star evolution and gravitational waves, and studying them with a combination of population synthesis of binaries and hydrodynamical simulations. In this talk, I focus on my work that has explored the detectability and properties of double neutron stars that will be detected by LISA using binary population synthesis. And the project involved a number of collaborators, including my supervisor Ilya Mandel, and Alejandro Vigna-Gómez, Coenraad Neijssel, Stevenson, and Alberto Sesana. I'll start by giving an introduction on double neutron star formation, focusing on isolated evolution, which my work is based on. I will briefly mention the COMPAS rapid binary population synthesis code, which is developed by my research group and used in this study. Finally, I will discuss the properties and detectability of LISA double neutron stars and talk about what we may be able to learn about binary star evolution from detecting them. There are two main ways of forming double neutron stars that have a sufficiently tight orbit to emit gravitational waves that LISA is sensitive to, or more precisely, to have a sufficiently tight orbit so that gravitational radiation can drive the system into the LISA sensitivity window within the age of the universe. And these ways of forming double neutron stars are dynamical formation and isolated evolution. Dynamical formation involves interactions between unbound stellar systems, such as gravitational wave captures, flybys, and exchange interactions. They require an environment with a large density of stars, such as a globular cluster, and can form binaries that are relatively tight and eccentric. However, studies have shown that dynamical formation is only expected to contribute a small fraction of the overall double neutron star merger rate. And as a result, our study focuses on double neutron stars that are produced through isolated evolution, which is thought to be the dominant formation channel for double neutron stars. Isolated formation involves a pair of stars that are born in a binary, with a wide orbit such that the stars do not merge as their radii expand over the course of their standard single-star evolution. But they undergo this common envelope phase that significantly tightens the orbit to produce a final double neutron star that merges within the age of the universe, or reach the LISA sensitivity window in the age of the universe. The common envelope phase, shown here, occurs when the secondary star, which I define as the initially less massive star, overflows its Roche lobe and undergoes dynamically unstable mass transfer to its companion neutron star. Meaning the more mass that is lost by the star, the more its radius expands relative to the Roche lobe, leading to a runaway. The envelope gas piles up on the accretor and swallows the neutron star, forming a common envelope. Inside this common envelope, the neutron star orbits the stellar core, but spirals in as gravitational drag or dynamical friction dissipates the orbital energy. And this is used to unbind the envelope gas. The end result is that the binary orbit has tightened by orders of magnitude over only a dynamical time scale of the donor. And that donor star has been stripped of its hydrogen envelope. Another important stage to note here is this final supernova that completes the formation of a double neutron star. This supernova imparts an eccentricity to the binary orbit through a supernova kick. This supernova kick has two components. It has a natal kick from the asymmetric mass loss, and it also has a Blau kick, which is from mass loss that is symmetric in the frame of the exploding star, but not in the binary center of mass frame. The Blau kick actually dominates in this final supernova event, since the exploding star has already been so-called ultra-stripped by a mass transfer episode that follows a common envelope. And so it has very little envelope left for significant asymmetries to develop in the supernova explosion. And this makes double neutron stars interesting to study, for example, compared to black hole binaries, since black holes typically receive a very large fallback, and so produce little to no supernova kick. And they retain a mostly circular orbit at formation. And producing eccentric binary black holes would typically require some kind of dynamical formation or hierarchical triples. However, even though the double neutron star might be born with significant eccentricity, gravitational radiation gradually circularizes the orbit over hundreds of thousands of years or millions of years, depending on the separation of the double neutron star. And so what matters is whether these systems will have any detectable residual eccentricity when they enter the sensitivity window of LISA. This can be seen with a plot of the orbital eccentricity with the orbital frequency. A typical trajectory of a double neutron star through this frequency eccentricity space looks like this, where it is born with some significant eccentricity and gradually tightens and circularizes through gravitational wave emission, moving rightward and downward in this figure. By the time that double neutron stars are tight enough to emit gravitational waves that are sensitive to LIGO, the Virgo, and Coenraad detectors, they would have negligible eccentricity. And indeed, we haven't been able to detect any eccentricity in the double neutron star mergers that we have observed so far. However, since LISA is able to catch a glimpse of these double neutron stars when they were still emitting at lower frequencies of about a millihertz, these double neutron stars may still retain some eccentricity at detection. This is an animation that shows the same plot with eccentricity versus gravitational wave frequency, but each dot here represents a double neutron star with its properties at formation determined using binary population synthesis. In the limits of high eccentricities, the gravitational wave merger timescale scales as 1 minus e squared to the 7.5, and which is why we see sort of a shearing flow in this plot, where the more eccentric systems have a smaller gravitational wave merger evolution timescale, and so evolve faster. These double neutron stars come from the work of Alejandro Vigna-Gómez in his 2018 study, where he used the rapid binary population synthesis code COMPAS to evolve 1 million massive binary stars, of which only 0.13% form double neutron stars. COMPAS is a publicly available code that performs rapid binary population synthesis, and it takes only a fraction of a second to evolve a single binary from birth to death. It allows easy adjustment of its evolution prescriptions and model parameters, and it also includes Python tools for post-processing of data, such as to calculate metallicity-specific merger rates and to apply gravitational wave selection effects. And I've also put the website for COMPAS here, and you can get the code from this GitHub repo in this link. Now, to use COMPAS, one merely has to specify an initial distribution of binary properties at birth, such as separation, eccentricities, and mass distribution, and also prescriptions for your or model parameters to use to model the various phases of binary evolution that I've shown previously, such as the distribution of supernova kicks, what we assume about the efficiency of common envelope, and the efficiency of mass transfer, and etc. And COMPAS then outputs a population of compact binaries and their properties. In my study of LISA double neutron stars, I took the population of double neutron stars that was evolved with COMPAS in Vigna-Gómez et al. 2018, and I evolved them through the LISA sensitivity window and studied the detectability of these double neutron stars by integrating their SNRs. And we find that few tens of galactic double neutron stars may be detectable by LISA, assuming a 4-year mission lifetime and an SNR threshold detection, a signal-to-noise ratio detection threshold of 8. These double neutron stars have characteristic orbital frequencies of 1 millihertz, which corresponds to a period of 17 minutes, or a gravitational wave frequency of 2 millihertz if we have a circular binary. In our default model, we assume that the double neutron stars are distributed in the disk of the Milky Way. This figure here shows a particular Monte Carlo realization of these detectable systems with the LISA noise curve, shown in the black line. And the height of each dot above this black line gives the signal-to-noise ratio of these detections. We also found that LISA may be able to detect a few double neutron stars out to the Large Magellanic Cloud and Small Magellanic Cloud. And these are represented in the figure by the green dots. This plot here shows the eccentricity distribution of the LISA double neutron stars. This is a cumulative distribution where I'm plotting the fraction of systems with eccentricity greater than a value. And the different lines in the plot correspond to the results for various variations in our binary evolution model, with the fiducial model shown as the solid blue line. These variations are chosen to be rather extreme in order to understand the sensitivity of our results to the particular model of binary evolution chosen. And for our fiducial model, we measure a median eccentricity of about 0.1. And we also estimate that LISA may be able to measure eccentricities down to an uncertainty about 0.01 based on measuring the relative amplitude of the different gravitational wave harmonics that are emitted when you have an eccentric orbit. And in one of our model variations, we have assumed that the so-called case BB mass transfer is always unstable. And this is shown by the dashed orange line in the plot. And this has a noticeably more eccentric population of LISA double neutron stars and has a higher median eccentricity of 0.36. So let me explain what I mean by case BB mass transfer. It is a mass transfer episode that is initiated by a stripped helium star that has just completed its core helium burning. This is called a helium-Hertzsprung gap star. And in the formation of a double neutron star, this helium-Hertzsprung gap star was stripped by the common envelope events that it went through. And in our default model, we assume that this type of mass transfer is always stable, and therefore it strips the helium envelope of the star and leaves behind its metal core. But in the unstable case BB mass transfer model variation, we assume that all case BB mass transfer episodes are dynamically unstable, meaning it leads to an additional common envelope phase. This means that the binary is significantly tightened, producing double neutron stars that are born with about a millihertz orbital frequency. This is right in the detectability region of LISA, and so these double neutron stars have undergone very little to no circularization due to gravitational waves when they are detected by LISA. Being able to detect a subpopulation of these highly eccentric, unstable case BB systems can be very interesting. There have been papers proposing that unstable case BB mass transfer can account for the amount of hour process enrichment that we observe in galaxies. And also papers have suggested that the really massive LIGO double neutron star event, GW190425, could have formed from unstable case BB mass transfer. We then investigated the ability for LISA to measure the chirp masses of these double neutron stars. Having a reasonably good mass measurement is important to tell that the gravitational waves we're detecting belong to a double neutron star in the first place, as opposed to the tens of thousands of galactic double white dwarfs that LISA is also sensitive to. However, this may be difficult for LISA double neutron stars, because mass measurement relies on measuring frequency evolution. Yet, these double neutron stars evolve very little in frequency over LISA's 4-year observation period. And also, because these sources may have non-negligible eccentricities, their frequency evolution is actually driven by a combination of their chirp mass and their eccentricity. And so a good chirp mass measurement also requires a good eccentricity measurement. But we find that only half the double neutron stars have even any meaningful mass constraint, and by that I mean that their fractional uncertainty in their chirp mass is less than 1. But about a fifth of these double neutron stars, about 20%, have an uncertainty of 10% or less. And the best measured systems can have uncertainties of less than 1%. So to summarize, LISA is expected to detect few tens of double neutron stars. Most of them would be galactic, and perhaps a few could be detected out to the large and small Magellanic Clouds. This assumes an SNR threshold of 8 and 4 years of signal integration. And roughly half of these double neutron stars will have useful mass constraints from the LISA signal, with the best measured sources having their chirp masses determined within 1%. These double neutron stars have significant and measurable residual eccentricities with a median eccentricity of 0.1. And this might shed light on the uncertainties that plague our understanding of binary evolution.